Tim is, he's Tim, also Virginia Tech, situated in like the DC branch, if that's the right name. And he's going to talk about more graphics and fancy code stuff, and I'm just going to let you go with it.
Alright, thanks. So I'm going to talk, so the previous stuff I talked about was more in the realm of visualization. This is going to be a little bit of a departure. So we can talk a little bit more about tools for dealing with Bursty signals, and then get into using some machine learning techniques to try to learn some of these radio behaviors kind of from a very naive way. All right. This is our building in Arlington. I think a handful of you were there last night for Cyber Spectrum. And I just wanted to point out that this picture is almost near where the World of Beer across the street is. And so after the Cyber Spectrum meetup, several of you may have had a similar image to this. The Google Deep Dreaming filter, per se, applied to the image. All right. So, an outline that I'm talking about, I want to talk briefly about dynamic lambda blocks. This is a little bit further than the basic intro lambda blocks that I talked about last night. And for those of you that mixed it, I'll fill in that. I want to talk a little bit briefly about message-based modems, and then I want to get into some of the things we're doing with Piano and Keras to do machine learning on raw radio waveforms. All right, so the idea about lambda blocks is basically, in Python you have these lambda expressions. This is just an anonymous function pointer where you basically define kind of a functional expression that returns some output based on some input in Python. So here we have a simple lambda expression where we're saying the output of this function is simply the numpy FFT of x. So this is cool. We can write all kinds of quick little Python expressions, and then we can drop them into these stream lambda blocks and these PD lambda blocks, and these can be then dropped into radio waveforms very easily, just from GRC to do either stream or a message operation. So a quick example of that is here using a stream lambda block, where if you look here, we've defined the output to be the input port values times the conjugate of the input port values. And so this is just a x times x conjugate output, so we're computing a real power. So we have this sine wave coming in, and we have this constant magnitude of 1 coming out. So this is just a simple thing. If we didn't have a block to do this already in your radio, you could have just made it by writing this one line in GRC, which is kind of cool. So there's also, and that's kind of roughly what I showed last night for those of you who saw, but there's a cool extension to this with dynamic lambda blocks. So all you really need now is a setter, and at runtime I can just update whatever that lambda function is. And so here I have the same thing running. I've added some noise so that it's a little more visible, although it's not showing up wonderfully. So we have this expression up here, and we can edit it online. So if we want to do something like add a numpy.log 10 of this, that should work. So we now have a log scale. Or if we make this in abs, let's say an abs of this -1. All right, so now we have this like rectified move to 0 value. So this is just kind of a really cool way if you're playing with data to drop in expressions and play with stuff online rather than going through the whole. I mean, computer radio has kind of it's benefited from really rapid iteration. You can build a block and you can test it. And the fact that you can iterate really quickly is one of the reasons that we can move so quickly. And so this is just like trying to reduce that iteration speed even to a faster level. So you can just prototype stuff right here. All right. So we can build message-based modems based on this. So this is kind of a very happy modem. So you could throw this together in 5 minutes. And this is basically a message-based FSK transmitter modem that is simply 3 of these message lambda block expressions that you can just drop in and suddenly have an FSK transmitter. So here, first block, we're mapping zeros and ones to plus and minus ones. We're then basically doing an integer interpolation to number of samples per symbol using this numpy.tile. And then down here, we're mixing it by this complex sinusoid at the FSK deviation rate so that we're mixing it up to a standard FSK that you would want to see. And so this is a really simple FSK transmitter that you can write in 3 lines of code in GRC. And so, yeah, so I was going to point out, so there's 2 repos. There's this grFSK burst and this grPSK burst repo that have kind of example modems for these two up if anyone wants to go play with them. And Kieran did an awesome write-up on the PSK one, which he presented last night, and that's a link to that for anyone who wants lots of gory detail on how that works. So for demo, I just wanted to show briefly I should point out. So what we're doing here, we have these 3 lambda blocks. So a strobe block is just going to send out a random PMT. In this case, it doesn't matter. It's just a string test every 500 milliseconds into this random PDU generator, which is going to generate somewhere between 50 and 2,000 bits. And then we're going to insert a known preamble on the front. And then we go through our lambda blocks. So this one maps it to plus and minus 1. This one is going to upsample it to number of samples per symbol. And then this one is going to basically modulate it onto the carrier tone. So very simple FSK modem. We then drop it into an event stream source so that this is streaming out zeros constantly. And then whenever one of these messages comes along, it just gets dropped into the stream. And then we can do pulse shaping and transmit. So that's the whole FSK burst transmitter. If we look at it running, we can see on the bottom here, this is the raw bits for a single message each time they're being transmitted. And on the top, we have, once they're put into the stream time after the event stream sync. So this is just one kind of really quick way to prototype that kind of burst plan. All right. So GR Piano is something I talked about briefly at FOSDEM. And so Piano is a really cool library from University of Montreal. And basically what they're doing is they're taking NumPy expressions and they're taking the abstract syntax tree from the NumPy expression and then compiling it down into a CUDA kernel for you and then wrapping it such that you can make a Python function call, it passes your NumPy vectors down, executes this CUDA kernel, and then gives you the result back. So it's like the simplest way to write GPU code, basically. You're just writing NumPy, it goes and runs on your GPU, which is magical. So we can do this instead of the lambda expressions if we want, and actually drop in things that are going to go off on the GPU. So we showed this. There's a sine generator, a FIR filter, a fading model, an FFT, and a plotter. And so this all runs. There's some drawbacks to it in that we are going back and forth from the host to the GPU every time, which is super inefficient. And the Piano doesn't have really support for NumPy complex 64 types. And so you can add it, but they don't really want to formally add it until we can do full automatic differentiation of all complex 64 expressions, which is a slightly larger task to take on. And so this is a really cool model, but it really works best if you want to put some very large monolithic algorithm in one block rather than trying to go back and forth. So like a big CAF search in a Piano block might be really efficient and something you could offload. All right, so enter Keras. So Keras is a layer on top of Piano, and this provides essentially a bunch of deep learning primitives and libraries that can be used to build these different types of neural networks using Piano, but with a very nice, clean, concise API to do it. And so they implement neural networks. The whole idea of these deep neural networks in general is that they're doing their own feature learning. And so the first couple layers of these networks are learning these emergent feature maps, which come from the data and from being able to reconstruct the data through some regularizer. And so we get efficient backpropagators that come from carrots, and they implement both convolutional and recurrent layers, and a bunch of really great examples of how to use this stuff. Which I think it's probably one of the easier deep learning toolboxes to get up and going with. So the first kind of deep learning tool that we've been looking at, and I've been working a lot of this with John Corrigan, I should say, and so we've been going back and forth on all of this, but we'll speak to it here. So in a denoising autoencoder, the basic premise of how this works is that you're minimizing reconstruction cost. So you have this input training vector x, and this is essentially an unsupervised learning method, right? You don't have a class that you're training it to or some target value. What you're doing is you're taking x, you're corrupting it by noise, either throwing out samples or adding noise to those samples. You're then projecting it through a weight vector and an activation function into this hidden layer y, and then you're projecting it back down through another set of weights and an activation to this vector z. And your loss function for training this whole thing is you'd like x to be as close as possible to z. And so you're usually going to compute like a mean squared error between those two vectors as your loss function. And that's where you get your error gradient that you can do backprop from. And so this process, the fact that you're doing an autoencoder means you're basically going from x back to x, which is the reconstruction cost. And the fact that you're corrupting the values here before you do the input layer is the denoising part, and that acts as a great regularizer, and it really helps stochastic gradient descent avoid getting stuck in a lot of global minimas as well. And the fact that you're going through this narrowing hidden layer here, where y is a lower dimension than x and z in many cases, means that you're finding a low-dimensional representation of x. And so there's long been many ways to do dimensionality reduction, like PCA has been a very popular one for many years. But this is kind of interesting because it's a completely nonlinear way, depending on your activation function, to compress x into this hidden layer y. So it's pretty exciting to see what people are starting to use this for. So we started using this for just throwing some random, simple, structured signals into it, looking at what happened if we were to take the raw IQ data, basically constrain it through a narrow autoencoder, and then reconstruct the same IQ signal out the other end. So we're taking the signal, compressing it into this sparse representation, and then reconstructing it while using this denoising process. And so the two examples we have here are looking at throwing a dial tone signal, which is just a tone in, and throwing a QPSK signal, which is sampled at roughly 2 samples per symbol in. And so it's really cool here because if you look, basically the noise floor here has dropped in your dial tone by like 10 or 15 dB. And in the QPSK, we've seem to have reduced the cluster variance visually here in our signal. So that's why Shannon is up here in the corner going, WTF. This seems a little bit scary because we're not going to feed information capacity. Like information theory is pretty solid, but it makes you think, like, where is that noise going? And so I like to think of it as like, right now we have, some people will write iterative demodulators that'll do a demod, remod, or a decision-directed kind of thing. And I think that's really a lot of what's going on here, is you're kind of projecting these things onto the nearest manifold or set of weight vectors that's fit, and then you're reconstructing it from that basis function. So you're constraining your signal to lie along these bases that you've found. So we've done a lot of playing with this, and this is Corrigan's work right here. And so this is basically taking a noisy PSK signal in, learning these basis functions and then doing a denoise reconstruction in time. And you see that we can really smooth out and get rid of a lot of the kind of very sharp Gaussian noise here. And you can also see this case is particularly interesting because I think the hidden layer is roughly the same dimension as the input layer. And so there's a strong regularizer here being used, which is helping to really push the representation into a few strong representation or strong bases, right? All right. So, all right. So then, an obvious extension to this is convolutional autoencoders have been used widely as well, especially in the image domain. And largely, the idea in a convolutional autoencoder is that you might want to learn to recognize cats, right? Which I think was Google's first thing they did when they wanted to go with all this. And so that cat could occur at any pixel offset within a big image, right? And so you don't really want to just train a network that recognizes a cat, at this specific pixel offset. And so what we do is by tying these weight vectors at a bunch of different shift offsets, so like this weight here and this weight here will be tied, will be the same weight. So you reduce the parameter space of all the number of weights you're fitting, and you force this shift invariance property to the weights you're training. And so this is widely used in images. This is a great paper that talks about some of it. Yeah, so this one actually, this is Tara Singh's paper at Google, and this is one of the first papers that's really taking this and putting it back onto a time series data set. And so she's doing this on acoustic data for voice recognition. And instead of using the null frequency bins as they are, she basically trains the null frequency bins naively and winds up with slightly different frequency bins which perform slightly better than the raw null bins, which is really cool because we're now really training these networks all the way back to raw time sample data. All right, so what can we do with this? So we started looking at, what is a comm system? How do we use this, right? So one of the first things that comes to mind is finding preambles. So let's say that I know that some preamble is arriving randomly at me, and I don't know what the preamble is, or when it's arriving, and it arrives asynchronously, so I can't just integrate it out at some periodicity. And so what we have here is in blue we have roughly the preamble signal, and in red we have the, and this is worst case. And in red we have the signal plus a lot of noise, right? So this guy is pretty low. I think it's near 0 dB of SNR here. And so what we're doing is we train on a big corpus of 10,000 of these where it's the same preamble at a bunch of random time offsets. We train this convolutional network to figure out what these taps are. And then what you find is if you look at this second column here, these are the hidden representations. So we wind up with almost this impulsive thing where it's learned the preamble to be the weights for a single filter, and then it's roughly learned that a single impulse represents the occurrence of that pattern in the time series, which is really cool. Because basically this is a matched filter that it's learned naively what the taps are. So for denoising, what we can do is we can basically just take our input signal in red, project it up into this subspace, and then back down through those bases into this blue signal. And so you find that this red, really noisy signal, we basically, the blue one is the denoised version, and it seems visually to do pretty well, but there's not a lot of very quantitative metrics to speak to at the moment right here. The other really cool thing is this is a generative model. So we can basically build a modulator out of it. So if we now make a synthetic hidden layer where we set all the values to 0 and we just set 1 to 1, and then we run the network down, we can basically just transmit this preamble out as we learned it. And so we've now completely naively discovered this preamble. We can nominally find it, know what it is, and then send it if we want. So that's pretty cool. And if we wanted, we could go throw this into a traditional match filter. All right, so the last thing is looking at an FSK demodulator. And this is something we looked at, and so FSK is pretty easy. And this is, we looked at kind of the highest in our case. The question is, can these networks learn like, a basic way to just demap a complex FSK signal down into the representative bits? And so we came up with this relatively simple network here, which is linear except for this tanh nonlinearity kind of in the middle. And then we use dropout to do basically a denoising function. So you're losing half of your input samples every time you train this with stochastic gradient descent. And so it becomes robust to that kind of lost data. And so basically, we showed that at relatively high, reasonable SNR, I think this was in the order of like 15 dB, we were getting a 0 bit error rate. And so this was great. And it did not address all of the timing recovery and equalization methods. This was kind of just mostly a Gaussian noise case. So this is still like really early work, and there's all kinds of other things to continue looking at. But it was kind of a first pass of, hey, we can just build a demodulator with this without, going and looking up all the classical analysis. If we just know the input to output mapping. So yeah, there's lots more work to do here. I think the general idea is building generative models that can denoise and start modeling these sequences of radio signals in a generative way, and kind of substitute naively learned DSP mappings for our kind of expert customly coded ones. And the hope here is that we can really start to build these kind of radios with learned behavior that emerges based on data, rather than having to go and write a bunch of very specific DSP algorithms. And really the key here is just feature learning, right? So we want to do feature learning all the way from the data up, and not try to constrain ourselves with very specific features like kurtosis or things like that are widely used, which they're great, and sometimes they're very concise, but they also throw away a huge amount of information. And so I've kind of referred to that whole class of things as deep cognitive radio, but you can see how that one stands the test of time. All right, that's it.
Hang on time, so we have 5 more minutes to discuss stuff. Last question, and Tom ready. Last one?
Awesome. So the denoising, was that basically just Gaussian noise that you were denoising?
So a lot of times the denoising is done by just dropout. So if you have, n values in your input layer, you may just replace. So here at 0.5, you're replacing half of them with just a 0 value. There's a lot of different ways to do it. You can add Gaussian noise. I think for comms problems, like adding Gaussian noise might make more sense than dropout in some cases. So that's definitely one of the things I want to look at, is adding different kinds of noise injection methods that are appropriate for the domain into these models. So these were, a lot of these have been thought through in the image domain, more so in the comms domain. This is still a pretty young area in comms.
Yeah, because the follow-up question I was wondering about, since it's a nonlinear operation, if you could actually address nonlinearities in receivers and essentially recover through them, throw it up, through some compression plates in your receiver and see if you can actually, recover it.
Right, so I think that there's a huge potential here to do that kind of approximation of these very expensive nonlinear operations. There's another paper that I don't think I referenced, where they're taking these they're like ONQ edge-aware filters for image processing, and they're too expensive to run on automated platforms, but they simply train a nonlinear deep neural network to approximate that filter, and once it's trained, they actually have a much lower computationally complex filter, which is like 99% equivalent in the input and output values, which is really cool. And I think maybe we can do that for a lot of operations in comms as well. So yeah, I'd like to look at some of the expensive FEC algorithms and see if there's like nonlinear ways to get there faster with less cheap iteration.
Have you thought about interference, not just noise?
Where are you?
Over here.
Interference in what regard?
Instead of just doing noise, how about interference?
Yeah, so I definitely want to look at like co-channel separation problem. I think that there could definitely be a fruitful application there as well. I think spatial and separation kind of applications of this are ripe for all kinds of great work.
Okay, if there's no more questions, I'd like to thank the speaker one more time.